All right, so these are the test 3 review problems. We're going to solve these. All right, so for number 1, we have to figure out the escape speed from the surface of a neutron star in terms of the speed of light. In other words, we'll get some number times the speed of light. And like in this is just an example. So for 0.53, right? Times c. So in Blackboard, of course, you just put like 0.53. That's if that was the answer, which it's not. We're going to do that. All right. So anyhow, if the mass of the neutron star is 1.84 times the mass of our sun, and the radius of the neutron star is 10.2 kilometers. All right, so we have to figure out the escape velocity. And of course, we're given this information, and of course, you'd be given this type of information on the test. The mass of our sun is 2 times 10 to the 30th. Of course, one kilometer is 1,000 meters. And they tell us to round to 2 places past the decimal. All right, so that's what we're doing. And let's switch this up. All right, so here we go. Here's the escape velocity. Those are our numbers. We know the mass. So we have to put that in terms of the mass of this, so anyhow, the mass of the sun. Here, let's do this. So m is going to equal 1.84. That's an 8 times 2 times 10 to the 30th. Oops, 2 times, 10 to the 30th. Of course, that's got to be the mass has to be in kilograms. Sorry, I didn't do this very well. All right, so let me pause and get my calculator out. All right, so here we go. Let's see, I just had to get my calculator out. All right, so multiply 1.84 times the mass of our sun, you get 3.68 times 10 to the 30th. And of course, that's 30. Sorry, it looks like a 30. It's times 10 to the 30th. Sorry. All right, so that's the mass that we're going to use. And then R is pretty trivial. We just had to change kilometers to meters, so it would just be 10.2 times 10 to the 30. Times 10 to the third meters. All right, so that's pretty much everything that and of course, big G is what it always is the universal gravitational constant, which is 6.63. 6.67 times 10 to the minus 11th. All right, so here we go. So the escape velocity, right? Let's just write this out. The escape velocity is, don't forget, you got to take the square root. All right, so this is the square root of 2 times 6.67 times 10 to the minus 11th. All right, and then the mass that we just figured out, and let's see, we need more room here. So here, close parentheses, open parentheses. The mass that we just figured out, which was 3.68. And remember, times 10 to the 30th, you could also write E 30, right? That means the exact same thing, divided by, so it's 10.2, so 10.2, and then, times 10 to the third, or E to the third. It means the same thing, right? The key thing is R has to be in meters. All right, so give me a second, and I'll put this in my calculator. All right, so you put all this in the calculator, and this is the answer that you get. So it's where's my cursor? All right, sorry, I couldn't see the cursor. So it's 219,382,377.3 meters per second. Of course, that's the answer, but that's not the way that they wanted it later. Let's look back at the problem. It says hint don't put the value of c, just give the number that would multiply c to get the escape velocity. All right, so we're going to get some number. It's going to be a fraction of c. All right, so I'm going to show you how to do that. So we're going to take, here, let's go back to this. We're going to basically take this number right here, this, this is basically 2.19 times 10 to the 8th, right? I mean, you can see that, right? Move the decimal place, 1, 2, 3, 1, 2, 3, and then 1, 2. So 2.19 times 10 to the 8th divided by 3 times 10 to the 8th. That'll give us the fraction. Remember, this is a neutron star. So this is just below the speed of light. All right, so this thing's, it's not quite a black hole, but it's getting really close to being a black hole. All right, so give me a second. All right, so I paused it for a second. So we're going to take this number, which was the calculated escape velocity, and then we divide it by the speed of light. Notice, of course, the meters per second cancel. Here, let me do that with my stylist. So the meters per second in the numerator cancels the meters per second in the denominator. And so we just get a number, and they told us to round it to 2 places past the decimal. So I get 0.73. All right. So in other words, this is the escape velocity is 73% of the speed of light. Right, so that's here's another way to write it. So anyhow, this is 0.73 c. But really, all we want to write in Blackboard is 0.73. Right, that would be the answer. That would be the correct answer to put in Blackboard, because they want to know what it is in terms of the speed of light. So really putting 0.73 would be the correct answer, right? 0.73. All right, let's move on to the next problem here. So here's our next problem. We have a white dwarf, and it has a temperature of 16,077.8 Kelvin. Its luminosity is 0.037 times the luminosity of our sun. What is the radius in solar units, i.e. that is, the radius is equal to what times the radius of our sun, and it says round to 3 places past the decimal. All right, so let's do this problem. All right, so taking the information from the problem, here's the temperature of the star. It's usually given T asterisk. So this is of course we have to square it. There's, of course, the temperature of the sun, 5,800. We have to square that. In this case, I did. You can either individually square the temperatures, or divide the two and then square the fraction. Anyhow, the temperature of the star is 0.037 times the temperature of the luminosity of the star. So this is a white dwarf, of course, is 0.037 times the luminosity of our sun. And then, of course, in this equation, it's it's the square root of the luminosity of the star divided by the luminosity of the sun. Remember, this is why we always report the luminosity of the star in terms of the luminosity of the sun, so that the luminosity of the sun cancels. Let's see, am I in there? Yeah, there we go. So this should cancel. And then, of course, the temperature in Kelvin, the Kelvin cancels. And so let's do this. So this is just a number times the luminosity of the sun, right? Don't forget to square this. All right, so it's 5,800 divided by 16,077.8 times the square root of 0.037. All right, and so let's see. I think the problem, they said to that's the equation that we're using. And so it says to round to 3 places past the decimal. All right, so we're going to round to 3 places past the decimal. All right, so make sure you put all this in your calculator correctly. So this is what I get in my calculator. I get, so 3 places past the decimal, it's going to be 0.025. It's 0.025, and then so that's what you put. That is what you put in your calculator, and then of course it's it times the radius of our sun. So this is much smaller than the sun, but remember the thing that you're putting in Blackboard would be the 0.025. All right, let's look at the next problem. All right, so the next one, what is the distance in parsecs of a star? Of a star that has an absolute magnitude of negative 1.4 and an apparent magnitude of 6.96. And of course, that one here's the equation. Let's see. Where's the equation for that one? Right here. So here's the equation that we're going to use. So that little m is the apparent magnitude, capital M is the absolute magnitude, and then you say plus 5, and then that entire thing divided by 5, and so the answer is in parsecs. All right, let me write that out. All right, so here's problem 3. There's the apparent magnitude, there's the absolute magnitude. Of course, remember, it's minus a negative. And so, and then you add 5, and then you divide the whole thing by 5. It turns out to be 10 to the 2.672, and then they told us to round it to 1 place past the decimal. So what you're entering in the calculator would be 469.9. It's like 0.89. So you'd enter 469.9. Okay. 469.9, and the answer, of course, they want the answer in parsecs, right? And of course, if you had to change it to light years, you'd multiply it by. So let's just say it was changed to light years. You'd multiply that by 3.26, right? So times 3.26. I mean, we don't. It doesn't say that to do that in the problem, but here it is in light years. It would be 1,531 point. So if we rounded it to 1 place past the decimal, it's like 0.85. So I'm going to say 0.9, and then of course that would be light years. All right. So it just depends on which one, and of course we're using this conversion. The fact that 1 parsec is 3.26 light years. All right. Okay, so let's do the next problem. Let's just go over here. All right, so next problem, we have a stage 4 protostar, has a temperature and a luminosity. They give us the temperature, they give us the luminosity. What is the radius in solar units? So that's exactly like we did before. We just used this temperature, 3,510.8, and this luminosity, much more luminous this time, 5,120.6. All right, so let me set that problem up. Let's see, do I have enough time to do this one? Actually, I'm running out of time. Let me, let's see. So, all right, so I'm running out of time, but so this is the radius of the protostar. The little asterisk here is in this case, is a protostar or the star. So it's the square root of the luminosity, divided by the luminosity of our sun. So that cancels. There's the temperature of their sun. There's the temperature of the protostar. You square that fraction, and anyhow, you get 193.3 times the size of our sun. So so in Blackboard, of course, you'd put it says to round to 1 place past the decimal. So 100 195.3. All right, so that's problem number 4.